Hello students, we are meeting for our next lecture and in the chapter manufacture of basic chemicals. In the last lecture we have started manufacture of nitric acid and we have seen how nitric acid is very useful and it is similar to sulfuric acid. Nitric acid is also very important chemical in manufacture of many other industrial products. Under that you can see there may be synthetic fibers, dyestuff, explosives, that all were discussed in the introduction part of the manufacture of the nitric acid, that why it is necessary to study manufacture of nitric acid. And we have seen that this manufacture of nitric acid is carried out by Ostwald process, which involves ammonia oxidation process, that all of you know. So what is this Ostwald process that we are going to discuss? Under that we have seen what are the raw materials for this process, that is dry ammonia, air, water and platinum rhodium gauze as catalyst. Then we have seen what are the chemical reaction. Actually these chemical reactions, these are the steps involved in manufacture of nitric acid. The first step is oxidation of ammonia to nitric acid with air or oxygen in presence of platinum rhodium catalyst. The reaction is shown here. All of you can see that reaction is exothermic, and so therefore there you can understand the physico-chemical principle behind it also, that we are going to discuss separately. The second step is oxidation of nitric acid to nitrogen dioxide. It is similar to sulfuric acid where SO2 has to oxidize to SO3. And this reaction is also exothermic. And the third step is absorption of NO2 by water, that is hydrolysis, which converts this NO2 to nitric acid. This hydrolysis or treatment with water is also exothermic process. If in this last step directly air is used, then the reaction is also given at the end of the this slide. So here the mainly three steps are involved. The same three steps are taken care while manufacturing of nitric acid. So up till now we have discussed in last lecture. Now we'll see the actual process of manufacture of nitric acid. And for this manufacture of nitric acid, the flow sheet is like this. That air, you can see here, air is one starting material, whereas very important starting material, that is ammonia. Now in the same chapter, in the beginning of this chapter, we have seen how ammonia is manufactured. Ammonia is prepared by Haber's process. So directly that ammonia cannot be used for manufacture of nitric acid. So what you have to do, ammonia prepared by this Haber's process is to be scrubbed in sodium hydroxide first, okay, and then freed from water, means it is purified. Okay, so how it is freed from water? By refrigeration. Okay, and then this ammonia is further purified from oil and ferric oxide. So before giving the input of ammonia, the ammonia has to be purified in this way, and this purified ammonia is vaporized in continuous steam evaporator. You can see here there is one evaporator. So this ammonia is evaporated. So the reaction is carried out in gaseous medium. Now the another important starting material or the reactant is air. Okay, so this air is compressed to 6.8 atmosphere, then it is filtered and preheated to 300 degrees Celsius. Okay, how it is heated? By passing through heat exchanger. So this preheated air which is compressed at 6.8 atmosphere and filtered is sent to compressor. That is one more reacting material. Okay, so this ammonia is mixed with purified and preheated air in the proportion of 1 as to 10 volume. You can see in the last slide we have seen that lot of oxygen is necessary for this oxidation of ammonia. So this oxygen, the source is air. So for this reaction, ammonia and air are taken in the proportion of 1 as to 10. Okay, so this mixture of gases, when they are mixed, this mixture of gases is mixed in reactor. First they are compressed to 100 psi. Psi means pressure, pounds per square inch. This is, you can say, British unit of pressure. So 100 pounds per square inch. So up to that pressure this gas is compressed. Okay, so when all these gases comes in contact with each other in the reactor, what actually happens in the reactor? In the reactor, the reactor construction is, it contains the platinum rhodium catalyst gauze that were discussed, that which is going to act as a catalyst. So this catalyst, in the form of gauze, wire gauze, which is in hexagonal shape, and this hexagon has means the diameter of 16 inches. Okay, so such this reactor is comprised of this wire gauze in the hexagonal form of 16-inch diameter. Now it is fitted on horizontal grid. Grid means like your grills of window. Okay, so this on this grid, which is made up of nickel chromium steel. Okay, so on this nickel chromium steel, this hexagonal shaped catalyst is fitted. Okay, and then there is a electric current made available for heating arrangement of the starting material, so that reaction will start. Though the reaction is exothermic, for the initiation of reaction you have to heat it by using electrical heating arrangement, and once the reaction starts, the reaction itself is exothermic, so you can maintain that temperature from the energy coming out of the reaction. So what actually happens in reactor, which you can call it as a converter, the reaction is this: that ammonia reacts with oxidation at 750 degrees Celsius on the platinum rhodium catalyst, get converted to oxidized to NO and water, and lot of heat is generated when four ammonia molecules get converted to nitric oxide. Okay, so in at the beginning you have to heat it, but after that, when you reaction proceeds, once the temperature reach to 800 degrees Celsius, afterwards the temperature is maintained by heat of the reaction itself. Means you need not to supply any energy, so electrical heating you can stop, and this reaction helps itself to further conversion of the reactants. So this is the reaction taking place in the reactor. Now after this reactor, the output of this reactor is the hot gases. Okay, which are those? Then you can say nitric oxide will come out, then nitrogen gas which is unreacted, or you can say sometimes this ammonia, instead of getting oxidized to NO, get oxidized to nitrogen. Okay, that is loss of hydrogen, that is also sort of oxidation. So here NO, N2 gas and O2 gas and steam which is coming out of converter, these are the output of the reactor. Now what happens with this gas? These gases are passed through heat exchanger, or you can say cooler, which is very important. So after, when its temperature is lower down, then you can further it send for the first next step. So here cooler is very important. You can see here the cooler means output of the reactor. Okay, Now uh, these output, now after cooling, these gases are sent to absorber. You can see in the figure the last step is absorber. So what happens in actually in the absorber, the cooled gases from the reactor are introduced into stainless steel absorption tower. Okay, and then it is cooled externally with water, means it is surrounded by some water circulating system like our condenser. Okay, and here more air is added further for the oxidation of NO nitric oxide to NO2. Means here if at all some uh, if sorry, this is the second step, that is conversion of NO to NO2. So that is nitric oxide to NO2. Now here for that oxidation you have to supply extra air, that is extra oxygen. So what happens actually in this absorber, that nitrogen oxide get oxidized just by passing the oxygen gas. Now the gas is further cooled, means after this oxidation they are again cooled in S shaped condenser. Okay, so this S shape means it takes time, it remains for some time, and thereby effective cooling, and that too with by using cold water. Now the NO2 nitrogen dioxide form reacts further with water to give dilute nitric acid. You can see here. So when this nitrogen oxide is treated with water, it is converted to HNO3. Okay, and some amount of NO is still uh, remain, that is used again, you can recycle. Now you can see in all the three reactions, that is in the reaction in the reactor, reaction in the absorber, all the three reactions are exothermic. So you have to maintenance of the temperature is the important key step in this here. So waste gases are released from top of the tower. This is absorption tower, and nitric acid is obtained at the bottom, which is in the liquid form. Now here the product nitric acid which is obtained by this Oswald process is 61 to 65% concentrated. Okay, and the conversion of ammonia to nitric acid is 93%, means yield is 93%, but whatever you are getting, that acid is 61 to 65% concentrated. So in these steps actually the three important reactions or three steps are carried out in the process of manufacture of nitric acid. Now the last step uh, remains, that is see the product is, as I told you, is 61 to 65% concentrated. So you have to you have to go further for concentration of this nitric acid. So nitric acid cannot be concentrated merely by boiling. Means normally what we do, we boil any liquid, so that if the solvent is low boiling compared to desired product, that solvent get evaporated, and slowly the desired product get concentrated. But here it is not so. Nitric acid cannot be concentrated by boiling, because what happens, it forms a constant boiling mixture. Okay, uh, so you can you know that azeotrops, so azeotropic solution it forms. Okay, uh, so here uh, you cannot sorry remove water or make it concentrated just by boiling. So concentration of this nitric acid can be done by two process. One, in one process you can use concentrate sulfuric acid. Okay, so in this process concentrated sulfuric acid, nearly 93%, is supplied to the top of the silicon iron or stone ware tower. Means there is one tower which is filled with silicon iron or stone. So what happens, from the top you can add concentrated sulfuric acid. Okay, and the nitric acid, which is 61 to 65% concentrated, is just it is fed just below the top. Means at the top sulfuric acid, then your nitric acid. So when this nitric acid will trickle down, it will come in contact with our diluted nitric acid. So sulfuric acid will come down, and nitric acid will come in contact with that sulfuric acid. So what happens here? Uh, as you know, sulfuric acid is a dehydrating agent. So immediately it absorbs the water, and making the nitric acid more and more concentrated. So the vapors leaving the tower are 90% nitric acid. Okay, so this nitric acid in the form of vapor leaves the tower, and that nitric acid is 90% concentrated. And this H2SO4, which is initially 93%, after absorbing the water from nitric acid, the sulfuric acid becomes 70% concentrated. So sulfuric acid itself get diluted, and nitric acid get concentrated, and this nitric acid can be re-evaporated for the concentration purpose, or it can be used somewhere else if we need the 70% concentrated sulfuric acid. So sulfuric acid, its property of dehydration is used here, and the concentrated sulfuric acid dehydrates nitric acid and making it concentrated, and here the output is 90% concentrated nitric acid. Okay, this is one method. Then there is another method by which you can concentrate the nitric acid, that is magnesium nitrate. So in this process what happens? Magnesium nitrate 70 to 75%, okay, it is fed to dehydrating tray tower along with 65% nitric acid. Okay, from absorption power. Means here the diluted nitric acid is 65% concentrated, and magnesium nitrate solution is fed to that dehydrating tower. So magnesium nitrate acts as extractive distillating agent. It removes water at 100 degrees Celsius. Means you have to heat it, and when it comes in contact with magnesium nitrate solution, it removes the means first it extract that water, and then it is distilled off. Okay, so that is the role of magnesium nitrate. So therefore the magnesium nitrate method is used. Okay, so if you compare both the methods in comparison, the second method, that is concentration by using magnesium nitrate, is more superior than sulfuric acid method. The reason is, first of all, the cost is nearly half. Okay, and acid quality yield is quite better in use of magnesium nitrate. So though you can concentrate the nitric acid by both the ways, more useful or economical uh, concentration method is use of magnesium nitrate. Okay, so this is the total process of in the manufacture of nitric acid on industrial scale. Okay, so there are as you know, three steps involved, and that all the three were discussed. Now we'll move ahead, and we'll start the discussion of physico-chemical principles involved in this Ostwald's process. Now, in the previous slide, earlier slide, we have discussed that the manufacture of nitric acid by Ostwald process involves three steps. First is oxidation of ammonia to nitric oxide, that is NO. This nitric oxide is further oxidized to NO2, and this NO2 is absorbed in water to form nitric acid. Okay, so we have to discuss the physico-chemical principles for all the three steps, because each step is different. It is not like that for sulfuric acid we just discuss the conversion of SO2 to SO3, and we have try to find out the maximum favorable condition. Here what you have to think about the three steps separately. So, what are the principles involved in oxidation of ammonia to nitric oxide? So, here the main reaction yeah, for the of this step is ammonia get oxidized to NO and water, and leaving behind lot of energy, exothermic energy. So, and you can see the reaction is reversible. This reaction is, you can see, reversible, and forward reaction is exothermic. So here nine, as I told you, nine volumes of reactants are there. Okay, four volumes of ammonia, 5 volumes of oxygen. Okay, so there are totally 9 volumes of reactant, whereas if you go to the product you will get 10 volumes of product. Means here in the product volume is increasing. Okay, so so due to increase in volume, what will be the effect on physico-chemical principle, that we'll discuss. So under that first physicochemical principle for this step that we are going to discuss is effect of temperature. Now you know this reaction is exothermic reaction. So what happens? Lot of heat is evolved. So what happens to the temperature if we change the temperature? Since the reaction is exothermic, it is expected that low temperature will favor this reaction. That is expected one. But at low temperature, what happens? The rate of reaction becomes slow. So there is no uh, desired quantity of yield. So at low temperature, rate of reaction is slow. So on an optimum temperature for this reaction is 750 degrees Celsius, when the pressure is 6.8 atmosphere. I told you at the beginning, these reacting gases are compressed at this temperature. Okay, so here the optimum temperature maintained is 750 degrees. So at you cannot change this temperature at low temperature. At low temperature the reaction rate is low, and if you increase the temperature, there are chances of ammonia get oxidized to nitrogen, not to the NO2 or NO. So that chances are there. So to avoid that, you have to avoid the higher temperature than 750 degrees Celsius. So initially electrically heated, no, sorry, and second problem is decomposition of NO2. Thus the here NO2 which is formed can be decomposed. That is the another problem if you increase the temperature. So at higher temperature, not only ammonia get oxidized to N2, but decomposition of NO2 is also a big problem. So you cannot increase the temperature. You have to, experimentally it is found that 750 degrees Celsius is a optimum temperature, and the efficiency of process can be achieved by use of catalyst. The catalyst is only initially electrically heated to about 800 uh, degrees Celsius, and then reaction continues on its own. Means initially you have to heat externally. While discussing the reactor, I told you the temperature heating arrangement system arrangement is there, which hits the catalyst. Initially you have to heat, but as the reaction proceeds, the reaction is exothermic, so it itself is self sufficiently can maintain the 800 degrees Celsius temperature. So this is the effect of temperature. Now we'll see the effect of pressure. Now here reactant volumes of gases are 9. whereas in product is state. The forward reaction with little increase in volume, and backward reaction proceeds with little decrease in volume. So if you increase the pressure, equilibrium will shift to the small extent to left, decreasing the yield. Means here volume is increasing, means lowering the pressure is a favorable condition. Okay, so if you increase the pressure, obviously backward reaction will be dominated. So you should theoretically you should not increase the temperature, but there is some advantage of increasing the pressure. What happens, these reacting gases reactants are gases. So if you increase the pressure, the space velocity, that is volume of living gas corrected to normal temperature and pressure conditions, which passes over 1 cubic foot of catalyst per second. Means the quantity of gas exposed to the catalyst increases if you increase the pressure. Means these gases reactants get absorbed easily on the catalyst surface. Therefore, slight increase in pressure favors the yield of the product. The small proportion of catalyst is sufficient, and for the other reactions, increase in pressure shifts the equilibrium to the right. Okay, so here very important point is that the two factors, that is effect of temperature and effect of pressure, were discussed. Now in the next lecture we'll discuss the further uh, the rest of the physico chemical process involved in Ostwald process. So we'll stop here and we'll meet next time. Thank you.